Right. So, like, is mathematics, is it this like structure built on these independent truths, like a Platonic realm of perfect forms?
Right.
Or is it something we invented? Just, us playing around with symbols. I feel like that's been a question for like ever.
Yeah. And there are a lot of different ways to like approach that question.
Hmm.
Today, we're going to look at one that's, I guess you could say, pretty out there. Formalism.
Formalism. Our listener, you're the kind of person who likes to really understand these philosophical debates, and you shared some really interesting stuff from the Stanford Encyclopedia of Philosophy about formalism.
Yeah.
So this is for you. We're gonna really get into it. No like unnecessary jargon or anything, just straight to the point.
Exactly. We're going to try to figure out what formalism says about like the nature of math, what are the different types of formalism, what are the problems with it, and why are philosophers still, arguing about it.
Right. Like, does it hold up against the idea that math is like describing some objective reality?
Exactly.
Okay, so some people might think that math is just like a game, like, playing with symbols. When
Right.
you think about it, like when we learn multiplication tables, it's kind of like memorizing rules.
Yeah.
And then algorithms are just like, following a procedure.
Right.
It's like chess, but with symbols instead of pieces.
That's a good way to think about it. This idea, it's sometimes called game formalism. It does kind of capture how we like use math on a basic level. Like think about imaginary numbers.
Okay.
People used to be really skeptical about them,
Mm-hmm.
right? They just saw them as tools for calculation.
Mm-hmm.
And if you ask someone who doesn't like study philosophy about math, they might, describe it as like rules and symbols.
Mm.
But the encyclopedia entry says a lot of philosophers don't buy this game formalism thing. What's wrong with it? Well, the main problem is like if math is just a game,
Yeah.
then where does the meaning come from?
Right.
Like if it's just arbitrary symbols and rules, how could it tell us so much about the universe or even about like abstract structures?
Uh-huh.
It's like saying math is just an empty shell.
Okay, yeah, I get that. So game formalism isn't the only type of formalism, right? There's also Hilbertian formalism.
Right. And that's a more sophisticated view. It came from David Hilbert in the early 20th century. He said there's a difference between like the finitary parts of math, the stuff we can like really grasp, and the ideal parts, the stuff with infinite sets and things like that.
So like the ideal part is more abstract.
Right. And Hilbert thought we should be instrumentalist about it. Like the symbols don't really mean anything, but they're useful for reasoning about the finitary stuff.
Okay. So the ideal part doesn't really have like its own meaning.
Exactly. The idea was that the ideal part could conservatively extend the finitary part. Like any conclusion you reach about the finitary stuff using the ideal stuff, you could also, like, in theory, reach using just the finitary stuff. But maybe the proof would be way more complicated.
Right. But didn't Gödel's second incompleteness theorem mess that up?
Yeah, it kind of threw a wrench in the works. Basically, Gödel showed that any system that's powerful enough to do basic arithmetic can't prove its own consistency. Like it can't prove that it won't lead to contradictions.
Mm-hmm.
So Hilbert's plan didn't really work out.
Right. Big bummer. But we're focusing on the non-Hilbertian kind of formalism, right? The stuff that Frege was so critical of. What did Frege think people like Hein and Tomé were saying?
Well, it turns out Frege wasn't always the best at like understanding other people's ideas.
Mm-hmm.
He kind of attacked a straw man. He thought they were saying that math is literally just like making marks on a blackboard. He even made fun of them, asking if they wanted an infinitely long blackboard and an endless supply of chalk.
Wow. Okay. So what were Hein and Tomé actually saying?
Well, like Tomé used the word sign to mean representation, not just a physical mark.
Right.
So for him, infinite decimals were representations of like potentially infinite sequences, not infinitely long pieces of chalk. And he was also really influenced by Weierstrass's approach to analysis, which was all about like manipulating symbols algebraically.
So for Tomé, it wasn't just about like meaningless scribbles.
No, not at all. He thought of arithmetic as a game with signs. The signs weren't empty.
Mm-hmm.
It was just that like when you're doing calculations, you kind of ignore what the symbols actually represent. Like you focus on the rules.
Okay. So like you bracket the meaning.
Exactly.
So Frege was wrong about what these guys were saying, but why is his critique still important?
Because even though he was wrong about the details, he raised some really important questions.
Yeah.
Like even these formalists talked about, like mathematical domains and things like that. That suggests that there's more to math than just manipulating symbols.
Right. So the encyclopedia talks about two main types of formalism: term formalism and game formalism. What's the difference?
Well, game formalism is basically what we've been talking about. It says that mathematical statements don't really mean anything, or at least the terms don't refer to anything.
Hi.
It's just a formal system, like a game with rules.
Right.
And this is appealing to people who don't believe in abstract objects. Like they don't want to say that numbers actually exist.
Right.
Term formalism is a bit different. It says that mathematical expressions do have meaning, and the terms do refer to things.
Okay.
But they refer to the symbols themselves, not to, like, abstract numbers.
So like arithmetic is about the symbols 1, 2, plus, and so on.
Exactly.
But that doesn't really get rid of abstract objects, does it? Not really. Because you still have to deal with like all the different ways you can combine those symbols.
Right.
And that's an infinite number of things.
So, like, you've just shifted the problem.
Yeah, pretty much.
Okay, so if you're a game formalist, how do you make your view more rigorous? Like, how do you address Frege's criticisms about syntax and proof theory?
Well, you'd use the tools of metamathematics.
Hmm.
You'd start by defining a formal language, like what are the symbols and how do you combine them to make formulas? That's the syntax.
Okay.
Then you'd say what counts as a valid proof in that language. And if you can derive a string of symbols, like 3 plus 1 is 0, then in that system, it's considered proven.
Okay,
And you wouldn't need to appeal to like a external truth or meaning.
got it. But the entry mentions two big problems with game formalism: applicability and the meta theory. Let's start with applicability.
Right. This is a huge problem for any formalism that says math doesn't really mean anything. Like if it's just symbols, why is it so useful in the real world?
Yeah, why does it work so well in physics and engineering? Frege said, applicability alone elevates arithmetic from a game to the rank of a science.
That's a good point. Okay, so what about the meta theory problem?
So you have the mathematical system, right, like arithmetic, but then you have the theory about that system, the meta theory.
Mm-hmm.
And the problem is that the meta theory itself seems to be doing math.
Right, like you're talking about proofs and theorems and stuff.
Exactly. And those things seem like abstract objects.
Yeah.
So even if the object level math is just about symbols, the meta theory isn't.
Okay, so Frege really exposed some problems with formalism, but there were other formalist views after Frege, right? Like Wittgenstein's Tractarian formalism.
Right. Wittgenstein, he was a student of Frege and Russell.
Uh-huh.
But in his early work, the Tractatus, he had some formalist ideas. He said that mathematical sentences aren't really propositions. They don't have truth values.
So they're not true or false.
Right. He thought math was just a tool for making inferences between non-mathematical propositions.
So like propositions about the world.
Exactly. He even tried to ground arithmetic in non-mathematical language.
Right.
He said that numbers are exponents of operations. Like you apply an operation a certain number of times.
Okay. But how did he explain addition?
He said it was a rewrite rule involving operators.
Yeah.
Like m plus m means you apply an operation m times and then more times. But his system had problems. Like it couldn't really handle inequalities, and his account of multiplication was circular.
So it wasn't a very successful theory.
No, it only really worked for a small part of arithmetic. And in his later work, Wittgenstein moved away from this view. He had some even more radical ideas like finitism, but he never really solved the problem of applicability or the meta theory problem.
Okay, so what about the logical positivists? Like Carnap, they were influenced by Wittgenstein, right?
Right. Carnap wasn't exactly a game formalist, but he had some formalist ideas. He thought the philosophical analysis should focus on syntax and proof theory.
Okay.
And he had this idea called the principle of tolerance. He said we can create any logical system we want.
So like math is just one of many systems.
Right. And he thought this would get rid of like ontological arguments, like arguments about what exists.
Uh-huh.
But this raises some questions, like how do you tell the difference between empirical theories and mathematical theories?
Mm.
And how do you know if a mathematical system will be useful in the real world?
And didn't Gödel's theorems cause problems for Carnap too?
Yeah, Gödel's first incompleteness theorem says that there are sentences in arithmetic that are neither provable nor disprovable.
Uh-huh.
And that contradicts Carnap's idea that all mathematical sentences should be decidable.
Right.
And Gödel also criticized Carnap's need for consistency proofs.
Okay, so Carnap tried to respond to these criticisms, but it seems like formalism keeps running into the same problems. What about Goodman and Quine? They were really serious about avoiding abstract objects.
Yeah, they were hardcore nominalists.
Hmm.
They said the mathematical formulas are like beads on an abacus. They don't have any meaning.
So they really took the game analogy seriously.
Yeah, they did.
Yeah.
And they tried to develop a syntax that was all about concrete things. Like they treated mathematical expressions as physical inscriptions.
Okay.
But they didn't really address the problem of applicability. And there are also questions about whether their system is really consistent. Like, can they justify their claims about syntax without using something like induction?
Right. And what about sentences that are like really hard to prove or disprove?
That's a problem too. Like, imagine a sentence that says a really big number is prime.
Okay.
We might not be able to actually prove or disprove that,
Yeah.
even though it's definitely either true or false.
Right.
And for Goodman and Quine, that means the sentence is neither true nor false.
That's weird. Okay, so even the most extreme game formalism has problems, but
Yeah.
there's also term formalism, right? Like Haskell-Curry.
Right. Curry was trying to develop a non-Hilbertian formalism. He was really anti-metaphysical. He didn't want to say anything about what exists.
Okay.
He thought math was all about syntax, and he had a more rigorous account of formal systems than like Heining Tommy. He said that a sentence is true if it's provable in the system.
So like truth is just a matter of derivation.
Right. And he said that all of math is basically metamathematics. Like it's about what can be proved in different formal systems.
Right.
But this view is kind of close to structuralism,
Right.
and it doesn't really solve the meta theory problem.
Okay, so now let's talk about the Curry-Howard correspondence. That's a pretty cool idea. It connects logic and computer science.
Yeah, it's a really deep connection. It says that proofs are like programs.
Okay.
Like a proof of a logical proposition is a program of a certain type, and a program can be seen as a proof of a formula.
So like proofs and programs are the same thing.
Kinda, yeah. And this fits with the formalist idea that math is about manipulating symbols.
But does it solve any of the problems with formalism?
Well, it provides a new way to think about meaning in math. Like, the meaning of a proposition is tied to its proof. But proofs are still abstract objects,
Yeah.
so it doesn't really solve the meta theory problem.
Yeah.
And it's not clear how to extend this idea to all of math.
Right. Okay, so what about contemporary formalism? What's going on now?
Well, most of the recent work is in the Hilbertian tradition. Like, people have been thinking about the implications of independence results in set theory.
Okay.
And some people think this means we should treat some parts of math as ideal, like Hilbert said. As for game formalism, there aren't that many people defending it these days.
Uh-huh.
But there are some interesting views out there. Like Gabby had this idea of a lush middle ground formalism for arithmetic.
Okay.
And Azuni had this view where informal proofs indicate like maybe formal derivations. He's moved away from that now.
Right. And what about fictionalism?
Fictionalism is kind of similar to formalism. It says that math is like fiction.
Okay.
But not all fictionalists are formalists. Like Lang interprets logical consequence modally, not syntactically. So she's not really a formalist. But Alan Weir is a game formalist. He says that mathematical truth depends on concrete derivations.
Okay, so he's taking the concrete proof idea seriously.
Yeah. And that means that mathematical statements do have meaning and truth values.
Uh-huh.
But he still has to deal with the same problems. Applicability, Gödel, and concretely undecidable sentences.
Right.
He tries to solve these problems by saying that idealization is necessary even in metamathematics, and that formalists can believe in infinitely many formulas without believing in abstract objects.
Okay, so it sounds like formalism is still a live debate.
It is.
So to wrap things up, what are the key takeaways from our deep dive?
Well, formalism says that math is about symbols and rules, not about abstract objects.
Right.
And there are lots of different types of formalism, but they all face the same problems: applicability, the meta theory, and Gödel.
So a lot of philosophers are skeptical of formalism.
Yeah. But it's still an interesting view, and it has connections to computer science.
That's true. So, listener, you've now got a good understanding of formalism. You've seen how people have tried to make sense of math without believing in abstract objects.
Right.
And now, think about this. If math is really just about symbols and rules, what does that tell us about how we think? Is math like a reflection of reality, or is it just a tool that we created? This deep dive raises some really big questions.
Yeah, it does.
All right, that's it for today.
Thanks for listening.